So, first of all, thanks a lot for attending. And for those of you who are not Project Reactor users or Webflux users yet, but who plan to, this talk might be also helpful to convince you that reactive programming might be challenging, but we also have tools to solve the challenges. If you are not from Java world, but you want to learn what problems we had and how we solved them, it might also inspire you to try Java and some other things I'll be talking about very close to other languages as well. So before I start, I would like to, of course, say that what I'll be talking, although it reflects what we did at Pivotal, it does not commit to any future releases or something, and I'm talking about it as an information, not as an obligation. And a few sentences about me. My name is Sergei, as I was introduced. And I work as a staff engineer in Spring R&D team at Pivotal, and my project is Project Reactor. I'm also known for test containers. I'm co-maintainer of the project, and I'm really into development tooling. So I really like improving development experience. Also, I spent most of my career doing microservices, highly scalable systems, and so on and so forth. So I'm really happy to be here. So let's get to it. My first experience with reactive programming, and I think it reflects others' experience, was something like this. Okay. In my case, it was like this because of dreadlocks. When I started learning it, I was like, okay, I know runnables. It's just a standard element of something in Java. I want to run something. I can wrap it as runnable. So I was like, okay, mono from runnable. Nice. I can run some runnables with Project Reactor. I was like, yeah, okay, cool. I'll use runnable. But it was like this. Like, okay. Yeah. Why doesn't it work? What happens? Apparently, since I had to change the paradigm I usually develop and program, we were talking about reactive programming, and in reactive programming, we have a strong separation between the assembly time and subscription. And one of the first issues, and it's really silly, but still, one of the first issues you encounter is the need for subscription. Although it creates so many possibilities that it's really worth it. So once I learned it, 1 week later, I was feeling myself like, reactive seer. I was quoting Henrik Apfelmus and was talking about reactive programming like I knew everything. Of course, 1 week, that's enough to learn anything. But 1 week later, after we tried it in production, it was more like this. Like, yeah, okay, development time was great. I also learned some cool things. I was hearing about super highly scalable concurrent model of reactive programming. But in fact, our production was more red than green. And I would like to talk what could go wrong. So first surprise for me was that one of the things you feel like it's something you always knew are exceptions. It's so simple, yet tricky, because in Project Reactor, let's say you have such code, where you have some range of items that will simply emit 5 items from 0 to 5. Then you say, okay, I expect it to emit only a single element, the second line. And then I would like to perform the subscription on parallel scheduler. I'll be talking about this a bit later. Now, if we run this code, we'll get an exception. And the thing is, especially if we highlight the most important part here, our source was in com example demo package, but apparently there is no such in the stack trace, and it raises a lot of questions. Which source? Where is my package? And many other questions. So you try to analyze it, you see your production system failing, but you do not understand what's going on. So we have to talk about assembly and subscription concept in reactive programming. It applies to other reactive programming systems as well. But in case of Reactor, it looks more or less like this. First of all, you have assembly stage. Assembly stage means that you design your flow. You tell the system how the data should be flowing through the operators, through the system. You, in declarative way, declare how it should go. And then you go operator by operator. Nothing happens yet. We tell, okay, dot single here, but no exception will be thrown because we haven't launched this flow yet. We do other operators, and we finally reach subscribe. And when we subscribe, and it's the only way to run your flow, actually, when we subscribe, then we transition into subscription stage. And the subscription stage would be a bit different, because instead of going upside down, it's reversed. We subscribe to the last operator, and we go up, 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 and up. And to visualize it, it will look more or less like this. By the way, I didn't find a good emoji for subscription, so I will be using this kitty as subscription. So kitty is our subscription object, okay? Okay, so we return the subscription to mono-subscribe on. Then we do other stages, and we reach our range operator. Now happens the next stage or substage when our publisher gives us the subscription. And the same situation with subscription, so it would be fishy. So this fish goes down. And as you can see, everything happens in the parallel thread. Then when our subscriber will request some data, and that's important. In reactive system, nothing happens until you also request something. That's the principle behind backpressure. And when somebody is talking about backpressure, it also means that you request something, you get something, you control it. It's not uncontrolled. Then we request, and we finally reach our flux range, our flux.range operator implementation, and we say, give me maximum values you can produce. Now, this range operator will start emitting items. First, it will be 0, because we start from 0 to 5. All good here. We reach the end of the flow, we start emitting next one. All good here. Filter doesn't care. But now, when map operator will attempt to pass this value to the downstream operator, in this case, single, an exception will be thrown, because single operator has a special statement. If already got one element, then throw an exception. Quite simple one. But in case of this exception, we are not emitting, or we're not throwing this exception at subscription time. It happens later in a separate thread after we do some round trips with subscription and subscriber and so on and so forth. So there is a challenge how we connect this error to the original flow we designed it. And I would like to do a short demo to show you what we can do about it, because we have a solution. Please give me a second. Okay. Big enough, or I should make it bigger? Okay, cool. So what we have here, we have a standard WebFlux application from Spring, also works for classical stack. And we have just Flux, just hello world, and then this single operator. By the way, some people misuse single. They think that it will be the same as take one, and then last, let's say, where when you want to get the last item, the first item, but single sounds like it, so we'll be using single. Now, if we run this application, okay, our application started in 1 second, by the way. Sorry, I have a problem that I have to exit the presentation mode because terminal doesn't work for some reason. But if we do a request, and if we enter the presentation mode again, we'll see the exception already presented. As you can see, there isn't anything we can correlate with our source. We literally don't know what's going on. I mean, if it's the only single operator in your code, then maybe it's fine. But imagine a big service with many operators. Just there's no chance to understand where it comes from. So, in Project Reactor team, we also develop a lot of tools for testing and development, but not for production, because development time sometimes is critical, and when you develop something, you want to understand what's going on, maybe by paying a price of reflection or stack walking or something. So in this case, if we add hooks operator debug to our application, you can also put it in your tests, let's say, and if we rerun it, I can just open it here. Oh, nice. So now if we do the same, now it's much better. As you can see, we now have error has been observed by the following operators. And here we see single, subscribe on, and then some classes from Spring Framework. If we click here, we immediately get to the place where this operator was defined, and that's the operator which triggered the error. But if we run this hooks on operator debug in production, then you immediately spot performance regression. The reason why is because it's implemented the way we take a stack every time you use an operator. Let's say you write .map, and we immediately create an exception and get the stack trace, or use stack walker on Java 9 class. Even if there isn't any exception, you pay the price of the stack getting, and it's a very expensive operation. What we can also do in our production code, we can put some static helpers here. Let's say we want to checkpoint and say after single. And if we run this code again, also in production, now, it's not as good as it was with the stack trace, or back trace we call it, but at least we see that, okay, this error was observed by checkpoint identified by after single. And let's say if you have a lot of time, you can just put this checkpoint everywhere in your code. I would not do that because it consumes a lot of time, and also when you do it, you're not getting most of what you can get from this information. So the challenge we had is how to keep on-operator debug experience without paying the runtime cost. And for those who have Java experience, most probably you also experienced some APMs or some other technologies, Java agents, to instrument your code. And that's exactly the approach we decided to choose, because the APMs were there for many years. Their overhead is so low because you instrument your code. Basically, we are changing your binary result into the result we want to see, and then you're not paying any costs of stack walking or anything. So Now, if I go here and if I add reactor debug agent init, and if I run it again, we see the same information and even more. And I'll explain what else we see here, but how it works, actually. Okay, now I can drop this checkpoint. With reactor debug agent, we instrument your class only once at class loading time. It works really fast. And then after every operator, we add special, it's something like checkpoint, but with static information like demo controller, Java, what was that, 15, let's say. Now, we don't have to use the stack to detect where this operator was called from. We just instrument the call sites, and that's it. And we do it automatically. You can also see that we have even more data here compared to on-operator debug. Because thanks to the instrumentation, we also open a new world, a completely new world for us. We can analyze where it happened in the code. And let's say if you return something from your method, let's say using web client, and you return body to mono, so you're not actually doing any operators. Just you're telling web client how to create mono for you. And with operator debug, you will not have your code in the stack trace or in the back trace. But with reactor debug agent, we can see it here. Is identified by light checkpoint. And this place, if we go to this source, so no operators here, but we return monotype or Flux or some other core publisher from Reactor. And now we can also add the information here in case it helps. And sometimes it really helps, especially if you use web client. So, what we learned in this demo. First of all, checkpoint is the easiest way to help yourself in future. If you put some checkpoints, then you pay no cost in production, but you can identify some parts of your application. Then read about hooks on operator debug. That's the same concept behind reactor debug agent, just at runtime instead of a compile time. So if you want to know how it works and what it does, then read the documentation. But Reactor Tools provides the agent which can be used in production, and it's a huge advantage. And this is why I would recommend to use Reactor debug agent everywhere where you can, also because of the returns. Keep in mind that Java agent applies some limitations to what your application should be able to do. And there is also, for Java 8 users, you have to run GDK or use standard Java agent attachment mechanism. Because here, I was just using Reactor debug agent init, and that's it. But in case of Java 8 non-GDK runtime, you will have to use standard mechanism, or Java 9 plus works out of the box. And there is also a great article from one of Reactor engineers, Simon, who explains how assembly and subscription times works and focused on it. Let's continue. Now we have blocking calls. That's another even bigger beast because, well, exceptions, yeah, we can fix them. I mean, we just don't understand what happens. But blocking calls might actually destroy your system. And to understand why, and by the way, if your thread graph looks like this, you have a serious problem. So, how Reactor works. First of all, we have 3 default thread pools. Parallel thread pool is just a fixed thread pool with n threads, where n is the number of CPUs you have by default. You can also set a property. Then we have a single scheduler for the ones who want to run something or who want to redirect something to the same thread in case you have this limitation. It's usually used in UI applications maybe, or some specific needs. And there's also elastic pool. It's not limited, so it will grow forever. And it's recommended if you need to run some blocking code, but not all of them. If you ask which one, or do you know which one is used when we use delays, let's say, or some asynchronous task? Parallel. It's implicitly used unless you specify some other scheduler, but most of the tasks we do, or every non-instant task we schedule, is actually scheduled on the parallel scheduler. And in case you have non-blocking execution, that's okay. We just have some tasks, they're short-lived, they're not blocking the thread. Actually, we just do something, something CPU-based, not IO-based, and then we release the thread. So it's all good, we are happy. It's the best you can get when your thread graph looks like this. But when we have blocking execution, then we have a task. It will start 2 more tasks, and this task will be blocking. Let's say you're querying some other service. Then some other task will be scheduled. It will also start more tasks and more. Then another one will appear. It will schedule 4 tasks, and boom, we have a serious problem. Why? Because no more tasks will be scheduled until the smallest task returns. And let's say you're using parallel scheduler for timers or for web handling or something. And now you receive a new request from your API. And you think that, okay, we'll open the connection for this request, we will do something because we expect that there will be some thread available. But actually, there isn't such, and our users will be having issues. How to fix it? Well, obviously, use non-blocking APIs. And by the way, in another room, Mark, right now, we're talking about R2DBC. That's a new approach of doing databases, SQL databases access in Java. Sounds like JDBC, but reactive first. But you have another option, use custom thread pool. Just if you must do some blocking calls, then consider putting them into a dedicated thread pool. It will not be as efficient as it can be, but at least you will not be affecting other tasks in your system. So when we talk about scheduling, it's important to not be selfish, to not think that your task is the only task running in this scheduler, in this pool, because actually there are many tasks from many parts of your system all landing to the same pool. What makes it different between standard approach with blocking APIs and non-blocking ones. So we run more tasks. All they go to custom thread pool. As you can see, we have this second green box. It's scheduled 2 more tasks. But we had to wait until custom 1 and custom 2 threads are released. So we have more tasks, more and more. It's all good, because now parallel threads are ready to accept more tasks. But keep in mind that it's not a silver bullet, because delaying something in future means there must be some queue. And this queue will be an in-memory queue. Means that if you have a lot of blocking calls and they all go into the same pool, then the queue will grow and grow and grow and will eventually lead to out-of-memory exception. Let's do another short demo. So what I have here is this code. What we are doing. First of all, we are starting a range from 0 to number of processors we currently have. Remember, it's the same number as number of threads in parallel scheduler. We implicitly subscribe on parallel, and then we do some blocking operation. By the way, where's blocking operation? It's here. We await this latch, and it will block. But we also start another task with mono delay, and then when it's done, we'll release the latch. So it looks okay, and my computer, I think I have 12 virtual cores, so it means that it should be something like few seconds to run it, right? If I run it, first of all, let's simply release it and watch the threads. Parallel 1, 2, 3, up to 11. So our tests are running for seconds. What happens? Let's take a look at the threads. Apparently, all parallel threads are blocked right now. They're waiting some optimization, but they're still blocked. And one of these latch countdown will never be executed because of it. So we somehow, with this super simple code, managed to get a deadlock. But some users, especially the beginners in reactive programming, they think the old way, like, okay, I'll block something, but it's not a big deal. Maybe it will be a bit slower, but it will not destroy my system. But it actually might destroy your system, and that's a good example. And if we do like this, then it will be slower than we expected, but at least it will run fine, because there will always be one thread able to process the delays. But it looks more like anti-advocacy, right? I'm telling how bad reactive code is, right? Actually, it's not a problem of reactive code. It's more like a question of a color of the function. And there are two approaches. One approach is to have different colors of your function. Let's say blocking function will be one color, and non-blocking will be another. We can see it in, let's say, Node.js with await. And there is also Java, where we have functions of the same color. And actually, people think that it's better as long as you have good tooling to watch it. And speaking of the tooling, blocking calls are one of the hardest problems in reactive programming at the moment. This is why we created another tool. And this tool, this time, is not for production, although the overhead is really low, but the aim is more for testing or QA environments or staging environments. Here, I'll be using JUnit integration. And now, if I run this test again, so I put it back, and now we have, again, 12 tasks scheduled. But when I run it, I immediately get an exception. And if we look at the exception, we now see that we attempted to execute some blocking code from non-blocking thread. By the way, the tool works not just with Reactor, but other reactive frameworks or async libraries, or maybe just want your blocking code to be detected in your blocking application, why not? So it's not just Reactor. So now if we check what happens actually, then await itself is not a blocking operation. Like there isn't anything in await that blocks the JVM. But if we go down, we see unsafe park. And unsafe park is a native method. And this native method will take some time to process, and also, as we can see, it may block forever. There are many other blocking methods in JVM. We track them and we add them to our blacklist. But with this simple tool, quite simple tool, actually there is no chance your code will ever block, again, because you immediately get an exception, or you can record it with some callback. It's also supported in the library, and you can track the quality of your code and before you go into production and see red threads. So, the outcomes. First of all, please do not block non-blocking threads. It's really important, and it applies not only to Java, also to Node.js, to Python, to any other language we have, where we have non-blocking expectations. Things will get better with Project Loom. Maybe my children will be using it, maybe my grandchildren, I don't know. But I don't think that I'll ever get into production system where Loom is used, because it's a great effort, but it's also a huge effort in the JVM. It's like rewriting half of JVM because it was assumed to be blocking. But I'm really happy that they're doing it. Also, blocking calls are dangerous because they may sneak into your production system and you will not even notice. Let's say, okay, this -1, so if we use range of 0 to 5, then this test will pass. Okay, it will eventually release the log. But when you push it to production and you're running Kubernetes and you have only 4 CPUs, let's say, then the thread pool will be 4 threads instead, and it will block forever there. So keep your eye on blocking calls. And use BlockHound or other tools to detect them, because it's the best you can do. And even the most experienced code reviewer might miss some blocking calls during the review, especially when you migrate from your old blocking application to the new non-blocking one. And when you must perform some blocking calls due to database not providing a synchronous API or something else, consider using Elastic Scheduler, because it's not limited to the number of threads, and it will grow indefinitely. But it also means that it will eventually release the threads. One more thing about it. Some might say, like, okay, I'm using asynchronous APIs everywhere. Like, most of my code is asynchronous, and I'm safe. Like, I'm protected. Well, yeah, sure, it should be like this. But are you sure? Ask yourself, my asynchronous code, is it actually non-blocking? Raise your hand if you use Kafka, if anyone is using Kafka. Okay, cool. So in Kafka, there is a method to send something asynchronously. So it literally says that it will asynchronously send a record to a topic. So I read it, I think that, okay, I have a callback, maybe I have some Node.js experience or JavaScript experience. Callback means something happens in future and releasing stuff right now. So I got used to it. I know that callback means asynchronous. If you run it with BlockHound, however, you'll get this exception. And that's something I did not expect myself, and I bumped into this issue, and it was like, oh, wow. It's of course reported, and Confluent knows about it, and they are working on fixing it. At least I hope so, and to be fixed soon. But you never know, or you trust, but you have no tools to check, or there were no tools to check whether it's true or not. And if we go into this implementation, then what makes me even more scared that the algorithm will look something like this. Wait on metadata in send. Then we use max block time milliseconds when we call this method as an argument. It defaults to 60 seconds. And then if we go into wait on metadata, then it will be do while loop, where the most important part is remaining time starts with 60 seconds, and then we attempt to update and await for an update. Means that worst case, let's say you have some outage in your Kafka cluster or something, your code will be blocked for 60 seconds. Now you're sending from 4 threads, and you're blocking your application for 60 seconds. No more I/O, no more timers, you're blocked. Yeah. It's okay to trust the libraries you use, but also always check what you're using, and we are all developers. We all make bugs, and we also fix them, or we believe we fix them. But having tooling never lies if it works, of course. So don't trust your tooling entirely as well. But at least if we have tooling, if we have tests, then we can verify that, okay, this method is actually not blocking. And I would like to show a bit more of tips and tricks for the Reactor users out here. There aren't many, but at least for the ones. There's another thing about reactive programming. We talk about backpressure, and this also applies to any reactive framework, or most of them. And it means that, remember I said that there is a request. And if we request 5 elements, then we expect 5 elements. And if we didn't request anything, then we will not get anything. So let's check how it works. So let's subscribe on our source. And this source is a super simple one. We just generate an infinite stream of integers where every new emission is last one plus 1. And we log every generating attempt. Now if we subscribe, we'll subscribe, and there is no take, nothing like this, so we're just getting a lot of items emitted at very high rate. However, if we subscribe with reactive subscriber, let's say, and we never request anything, if we never request anything, then of course we should not get any generating line in the log. So all good here. It works. After all, that's reactive specification, and people were working on it like many years. Now, if we request 1 element, we get 1 line, obviously. And if we request 5 elements, we get 5 lines. So, works perfectly fine. That's what specification says. And so far, we never reached the part where specification becomes, or where things becomes unspecified. And one of such things is prefetch. And prefetch is a mechanism to optimize your code by prefetching, obviously, some data upfront. And most of the times, you don't care about prefetch, it just works, and it's totally fine, unless you go to distributed reactive streams. But it's also a bit unexpected, because if we do concat map, let's say, so we just want to start another publisher and immediately subscribe on it, just mono from. Sorry. Oh, sorry, not from one just. So we run it. What will happen? Wow, it's actually how many? 32 matches of generating. What happens? I've been told that unless I request something, nothing happens. But here you see prefetch in action. Although you haven't requested anything, there is also lazy prefetch to make it faster when you request. And when you request something, let's say 5 elements, then still 32, unless you request 33. That's an optimization, but it's really unexpected one. But if you want to understand your system better, then there is a very simple operator. It's the simplest operator out there, but it's really helpful for debugging your reactor code because you can just put log source. And let's say you also want to log everything happens subscribe. Now, if you run this code, then we will see that there is a request to the source, and the amount is 32. And it's not just a magical number. It's not 42, okay? So it's just 32. But where it comes from actually is just the buffer we create upfront. And you can also control it, and you can also prefetch just one element. Why I'm focusing on it? Because now, okay, way less generating lines, because now we request 5 and prefetch 1. We get 6 in total, but it doesn't matter when you run in the same JVM. But if you start consuming from some I/O source like Kafka or maybe some other service, or use RSockets, then you should have it on your mind when you design your system that some operators will prefetch and use log just to see what's going on. So, reactive programming isn't easy, but very powerful. But when you do reactive programming, especially with Reactor, make sure that your production system looks like this and not like that, okay? So control your fire, and millions years ago when we started controlling the fire and changed everything, make sure that that's what's happening in your system. So, takeaways. I can just take a photo and save you a bit of time of me talking. But take a look at these tools, especially if you work with Reactor. But also, if you start with Reactor, BlockHound is a must-have, believe me. I did blocking calls. People still do blocking calls, as you can see on Kafka example. So it's not just something you can easily avoid. Yes, and feel free to contact me about Reactor and other topics. I'm always happy to hear any feedback, and always happy to help you, especially with your development experience. Thank you.
So, thank you, Sergei, for the cool insights into how Mono and Flux works. Are there any questions currently? There's one.
Hi, great talk. One question, how do you deal with databases if you don't have Mongo and if you don't want to use like experimental kind of reactive driver? There's no other option, or?
That's a good question. And first of all, yes, Mongo was one of the first databases to support reactive drivers and asynchronous drivers. But also now Couchbase is reactive, and others. There is also a reactive driver for Redis. And actually, in NoSQL world, reactive coverage is quite okay. At least asynchronous APIs are there. There is also an ongoing effort, I already mentioned, R2DBC, for providing the same experience for relational databases, because we do understand that, okay, NoSQL databases are cool, but actually people are relying on relational databases. Last but not least, if you have some blocking access, it doesn't mean that you must use blocking APIs in your code. You still benefit a lot from non-blocking web processing, let's say, if you use a reactive web stack. And we have Violetta working on Tomcat, but also on Netty. And the results we see and the applications we see with less memory footprint and faster responses is a thing, even if your database is still blocking. And last but not least, the database itself doesn't have to be reactive internally. As long as the client is reactive, it's already something huge. So it's just more the way you write your code and you design your system in a reactive way, and yeah.
Thank you. One more question here.
Let's say that you would like to add some tracing ID to each event emitted. Let's say you want to have tracing for your incoming stream of requests. How is it possible to do it with Reactor, with exclusion of course, adding another field to your model?
The easiest way is to use Spring Cloud Sluice. It's already integrated with Reactor, and everything you're doing with Reactor will be also forwarded to Zipkin, and you have distributed tracing out of the box just by adding Sluice to your application. There is also a concept of hooks in Reactor, and you can hook in any tracing you want, actually, and third answer to this question, actually, because there are many different ones. It depends on what you prefer. But we are also working on adding tracing or at least tracking capabilities to the Reactor core itself, so that even if there isn't library like Sluice for your preferred tracing system, or maybe you just want to do local tracing, something like this, then with just a few hooks, you plug in your own tracer. And the instrumentation part of Reactor is based on hooks. Take a look at hooks and scheduler decorators for this.
We have time for one more question. So then I have a question. How many people are working on Project Reactor currently, and how many contributors do you get from the community?
There are different teams. Team Reactor itself, we work on core and Reactor Neti. As I mentioned, Violetta is working on Reactor Neti. And then there are, so it's a team of 4, and then there are different teams like Spring Data and Spring Web, Spring Framework. They're integrating Reactor into the rest of Spring ecosystem. So we help them, but we are not doing these integrations. We're really focused on the core part. And in my case, I'm more focused into development experience and tracing as well, by the way. So if you have more questions, then I'm the one to ask about.
Okay, so thank you very much for your talk and the Q&A session. So just ping him afterwards at the dinner party, or yes. Thank you very much.
Thank you.